Hello everyone. In this video, I'll be describing the design and implementation of a SCADA system for the control lab flotation process. My name is Luando Keote, and I'm a final year student at the Department of Electrical Engineering, specializing in mechatronics. Okay, now this is the plant for this project. It's called the Flotation Process plant. What we have here is a total of 6 tanks, whereas the first 4 tanks are of the same size and the 2 tanks are larger than these 4 tanks. Now these 2 tanks are called the rougher and the scavenger tank. Now initially in this plant, water would flow from the rougher tank to the scavenger tank and back to the feed tank. And then this other part of the plant is a separate plant which has a recleaner, a cleaner, and another feed tank. However, for the purpose of my project, I wanted the plant to have a flotation between the rougher and the scavenger tank. And the reason for that is because these 2 tanks have the same volume, and then which means that if I would include this tank would overspill faster than these 2 tanks because of its smaller volume. Can you come closer? So the way I made the redesign of the battery limit of my project is that this pipe in here was connected to this pipe, which allowed water to flow all the way down back into the feed pump. Then what I decided to do was to remove this tank by disjoining these 2 pipes so that this pipe can move all the way down and back, feeding water into the rougher tank. So the results of the redefining of this battery limit is that we only have these 2 tanks, the rougher tank and the scavenger tank. And there's a feed pump which pumps the water from the scavenger back to the rougher. And you also have over here a valve, an automated valve, pneumatic valve that opens and closes from 0 to 10 in an analog step. We also have another valve over there, which is also an automated pneumatic valve. So this valve, we call it scavenger, and that one we call it rougher valve. We also have in the part of instrumentation 2 level sensors, which gives us the amount of water in each of the 2 tanks. So after explanation of how I redefined the battery limit of this plant, now let me explain to you how the plant is supposed to work. Now that we only have 2 tanks, we have scavenger tank and the rougher tank. So the water in this plant is supposed to be in a closed loop circulation flow. And that is done by feeding water from the scavenger tank with the use of the motor, the feed pump, into the rougher tank. So if we have 50% of water here, we're going to have another 50% of water here, where at initial conditions we would have filled 100% of water. And the control philosophy is that we want to control the height of the rougher tank. By doing so, if you want the height of the rougher tank, the water level, to go to 80%, the scavenger tank level will go to 20%. If you want the rougher level to go to 30%, the scavenger will go up to 70%. So in that way, we are able to control the height of the rougher tank. And this is happening by controlling the rougher valve. So if we open the rougher valve such that the output flow rate is the same as the input flow rate, that means that the output flow rate and the input flow rate are the same, and then the plant is at a steady state, meaning that we have reached the desired height. But then if you want the height to drop down, we'll have to open the valve such that the output flow rate is greater than the input flow rate, etc., etc. And also associated with the control philosophy of this plant, we have a safety alarm interlock. Now what we have here are 4 red flashing lights, and we also have a buzzer over here. We have a buzzer, and we also have a relay circuit that is also connecting the feed pump back into the control and supply panels. Now, what the safety interlock system does is, if the water reaches the maximum limit in the two tanks, then the safety alarm interlock will trip off this feed pump, and then the plant goes to a stationary condition, and then the alarms will beep, 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 and the buzzer also beeping high. And in addition to the safety interlock, we also have an electronics design circuit that are designed to allow the computer to be able to control these high voltage circuits. And what we have here is an amplifier circuit that amplifies the current from the DAC, which is a peripheral, into the PC, supplying the control signals. And then those control signals are being amplified to send control signals into the relay that controls the feed pump, the lights, and the buzzer. We also have over here a supply which allows a 1 ampere that will amplify the control signals from the PC. And the other component of this SCADA system design, we have two monitors, as I'll show you next. We have two monitors that displays in real time what's happening on the plant. So what we have is an animation that shows the level of water going up and down, and also graphical display that will tell us what is the actual error to the desired level of height. If our desired level goes to a set point of 100% and our current level is at 50%, that means the error is at 50%. Okay, now the setup is done as follows. So what we have over here is the supply panel, and below is the control panel. So with the supply panel, we firstly need to switch on the supply and another safety circuit. And then what we need to do next is to switch on number 4, the instrumentation power switch, which enables the level sensors, the valve, and the feed pump to work. So that is, we're going to switch on switch number 4. And you can see here that the control panel is on for the instrumentation. Next, we'll need to switch on the compressor over there. It's probably going to make sound because it needs to generate enough pressure to supply this pneumatic instrumentation. Now that's going to be switch number 8. Okay, now the next step is, before we can allow water into the plant, we need to open this tap so that water can flow into the plant. But there's two taps. There's this tap and another second tap, which is a safety tap. So now I'm going to start opening the tap. Now water is flown from this pipe into this other pipe, and it's being blocked by the second tap, the safety tap. Now once you open the tap, then water will flow through the pipe into the tanks, and then we're going to allow water to fill in both the scavenger and the rougher. When water is roughly 60% into the scavenger tank, we'll switch on the feed pump so that water can be pumped into the rougher. And then we want the water into the rougher to be 30%. That sums up a total of 100% of water into the plant, so that we can be able to control the height of the rougher tank with a total of 100% water in the plant. Now let's go switch on the pump, the tap. and then we can start the demonstration of controlling the level of height in the rafter tank. Okay, now so I will show you the different softwares that are working for this project. So here, Visual Studio. Now Visual Studio makes use of C# by collecting data from the plant, and the data is then written to a database, and the database that is being used here is Microsoft Access database. We have this first table where we're writing data, and the second table where we're reading data from the HMI. Now, in order to connect the HMI and the database, we need a server, and this project makes use of this server and an OPC communication protocol. Now you can see here on the server, we have the last entered value for the desired height was 74%, and the last entered value for the scavenger valve was 10, which is fully closed. And now this OPC communications protocol allows the database to communicate with the HMI, where we have here the animation HMI and also the real-time trend, which will illustrate the graphs of the data in real time. And now next we'll be running the plant and the HMIs so that you can see how we can monitor and control the plant, and also allow a safety feature into the plant. When the alarm is high, we have also here a button for alarm resolve, where we can say let's switch off the alarm so that we can assess the issue. Once we switch off the alarm, the control circuits will switch on the feed pump, but what we need to come to the supply panel and switch off the feed pump manually. Now let's get on into running the plant and able to see how the two HMIs operate, controlling the plant in real time. Okay, switch it on, turn it on. Okay, so right now what we're doing is turn more again. To max. So right now what we're doing is filling in water into the system. We want the water to be total of 100%. So if there's 60 here, we want 40 there. You can also see on the HMI, the level is going up. Now you can see the scavenger is at 15%, 16%, 18%, and you can also see from the graphical HMI, the scavenger level is going up with blue trend line. Okay, so now we have the setup already. We have the HMI 2 screens ready. We have the alarm interlock system ready. You can see here the supply of the alarm interlock is on. We have now liquid water into the plant. We have redefined also the piping, and the communications have already been developed. The database, the OPC communications, and the server as well. Now we'll show you how we're controlling the plant from the HMI screens. So now we're going to switch on the feed pump. We have over here the desired height at 48%. The current height is at 31%. And you can see the error is also going down as the rafter tank reaches the desired height. Once the rafter tank is equal to 48%, you'll see the error trend line going down to 0. So now you can see the rubber tank is at a constant level. That means the system has reached the steady state. And if you come over to the HMI to monitor the plant, you can see that the rubber tank is actually at the desired level, the 48%. And you can also hear the sound of the valve opening and close, such that the output flow rate is the same as the input flow rate, keeping the height at a steady level. And you can also see here that the error is now 0. Next, we'll control the height once more to, let's say, 60%, 63%. And the rubber tank is supposed to go up again. Now you can also see the level of the height from the rubber tank is also slightly going up. And also the moment we've applied that control input, we have seen a rise into the error. And now the error is gradually going down. The blue trend line is the set point, which was that 63%. The yellow line is the rubber tank height and is getting closer and closer. Now you've seen the sound, meaning that the rubber tank height matches the set point and the error is 0. Whereas this line is for discovering the level height. And now we can also see from the displays, we have now reached the steady state. Okay, so now the next step is we'll try to see the working of the alarm and safety interlock system. And how we're doing that is from the HMI set point control input, we'll set the desired level to, let's say, 91% or let's say 95%. So now the desired rubber level is set to 95% and the current level is at 14%. So we're expecting the rubber level to go up but not to exceed the maximum limit. Once it reaches that limit, then the alarms will switch on, the buzzer will sound, and the relay module will switch off the fuel pump. And the valves will also be closed so that the issue can be assessed. Now we have refreshed the HMI, but the data being displayed is still the same. So the desired rubber tank height is at 94%. The rubber tank height currently is at 72%.
Yeah.
And the water is being pumped right now on a big pump into the rubber tank, trying to reach the set point. As you can also see from the graph, we have the yellow trend line, which is the current level, the blue line, which is, and now what is happening is the feed pump has been tripped off, the alarm is, the flashlights are on, and the buzzer is on, which means that now the maximum level has been reached, which is 80% of the rubber tank height. So this usually happens whenever there's a malfunction in any process plant, and an engineer inside will have to come and resolve the issue. So how we do this is we have to switch on the alarm resolve, which says trying to resolve the issue. And we also need to switch off the feed pump, and then we can then assess the issue and solve any problem if there's any malfunction within the process. Alright, so as you have seen, we're able to control the level of water in the rubber tank with the use of the HMI by supplying control input, a desired control input into the HMI, and allowing the system to automate itself into that desired level. And the used controller for this plant was the PID controller, and a PD controller particularly. Normally in the industrial space, a PLC controller would be used, but for this project, the most accessible controller was a PID controller, which can easily be implemented with the use of a programming language. In conclusion, the diagram that you see here summarizes the breakdown of the SCADA system design, which is made up of 3 subsystems, namely the data acquisition and data management, monitoring and control, and the safety supervisory control. And these are made up of a total of 5 sub-module designs. When integrated all together, forms the SCADA system design of this project. And as you have seen also on the demonstration, the SCADA system design was successfully designed and implemented successfully as well. And with the use of a SCADA system, businesses and governmental entities across the world have become more than data-driven in making profitable and effective decisions for their industrial process plants. And these includes the mining, metals, minerals, and the infrastructure industries. And not only is SCADA systems constrained into these industries, also goes broadly into robotics, piloting, which forms part of manufacturing, and traffic control. And in closing off, I want to thank everyone who has played a very essential role in helping me when I needed during the setup and etc. To my videographers, to my supervisor, to my colleagues at the control lab, my classmates at the Department of Electrical Engineering. I want to say thank you to everyone until this project was a success, and thank you as well to you for watching this video, and until next time, thank you for watching.